Morning, Eric. Morning, Azra. Morning, Hike. Morning, Kimberly. Hi, Charlie. Hi, Logan. Hi, Ryan. Hey, Ava. Anyone else who's watching? Good morning. Eric, I would go fill out the attendance form. Figured it'd be the quickest way to tell you to do that. So, today's agenda, we're doing DNA number 2. I'm going to go over this project that we're getting into again, the guided science application on exoplanets. So applying what we know about the solar system and objects in the solar system. And then you're going to begin phase 2. So we'll do phase 2 today and phase 2 tomorrow. Phase 2 for the first application and application C. So application A and C require some research. So you have 2 days to do some research. Whereas people doing application B, today you got to start building your spectrometer, which is pretty cool. If not a little difficult, because you got to make sure the inside of the box is completely dark, while at the same time making different cuts safely in a cardboard box. So, building your spectrometer, testing out to make sure it's actually able to refract light is the goal for today. Then tomorrow, you guys will collect data on different light sources. So, application B is hands-on, which is fun, but remember, you have to have those materials. You don't have to do it. If you have the materials, you can do whatever you want. But to do application B, you got to have the materials. I can't send them to you. I can't bring them into the classroom, unfortunately. Right? DNA sheet is due tomorrow before midnight. Only 3 DNAs a week now. Monday, Tuesday, Wednesday. We'll take our DNAC on Thursday. And Friday's time that you can ask questions and get things done on your own that you didn't get done throughout the week. No questions, we'll move on. DNA number 2. What is the relationship between a planet's mass and its rotational period? Again, is it a positive relationship? Is it a negative relationship? Or is it no relationship? A positive relationship, both variables like mass and speed of rotation would do the same thing. As one increases, the other increases. Or if one decreases, the other decreases. If they're opposite, it's a negative relationship. And then if they just keep going at random direction, like if one stays the same, the other one goes up, or one stays the same, the other one goes down, or if they just go up and down, there's no relationship. So knowing the difference between those 3 is going to be key, especially on your DNAC Thursday. Alright? You will have 3 questions about the relationships, and then you'll have 3 follow-up questions about outliers. So I'm adding a new term to your discussion of relationship, and that's an outlier. Basically, the exception to the rule. And that's another job of a scientist, is to figure out why that exception exists. Morning, Jake. Good morning, Nikolai. So see the attached data. I also have a small animation that I'll take a look at after we do our DNAC. Kind of helps you visualize what you're looking at in terms of rotational speed across the 8 planets. It's not to scale, it's not an actual picture, but helps you visualize the speed amongst all the planets. Alright, you'll be all good, Eric. But you still gotta fill out that form though, so we have a record. So I'm going to rank mass again and go through using scientific notation, looking at the power of 10, and then looking at the decimal to break a tie. And then we'll look at rotational period. This is in Earth days. So obviously Earth is set as one Earth day. That's how long a day is on Earth. Well then, what happens when you get a smaller number? What happens when you get a decimal, a fraction? That means Jupiter, Saturn, Uranus, and Neptune, they all have a day that is shorter than Earth's day. So their rotation is faster than the Earth. So if a number is smaller than 1, it's faster than Earth. If a number is larger than 1, it's slower than Earth, right? So a day on Venus is 117 times slower than a day on Earth. Saturn is close to half a day on the Earth. It's close to 12 hours, 11 and a half some hours, all right? So some of you should start to be able to see that your planet is involved here from toward the solar system. You should be able to remember the rotational period and see that, hey, yeah, Jupiter, largest planet, shortest rotation time. Y is what we're going to get at, all right? So I'm going to rank the mass in my chart. So again, you could make another chart, and you could make a chart for tomorrow too. Similar chart, just we're not going to do mass tomorrow. So we did mass yesterday, going to do mass again today, and then we have rotation, all right? I'm going to rank each one, each planet, from lowest to highest. And then do the same thing for rotation. So back to the chart. Who has the lowest mass? Well, we know Mercury's the smallest, 10 to the 23rd. I'm going to put Mercury as 1. Next smallest planet, we'll look at 10 to the 23rd or 24th. Mars, a little larger than Mercury at 6.39. 10 to the 24th, well, we both have Venus and Earth. Venus at 4 and Earth at 5 to 10 to the 24th, almost 6. So we'll do Venus smaller than Earth. Venus is 3rd, Earth is 4th. And there's the rank for the inner solar system. This is just the same as yesterday, right? Mercury, Mars, Venus, and Earth. We're going from the lowest mass, the lowest size, to the highest mass, the largest size, right? So then the gas giants are the next half. 10 to the 25th. Is there a planet that's 10 to the 25th? Uranus is the only gas giant 10 to the 25th. So Uranus is the next largest planet after Earth. At 5. Number 6, we'll go to 10 to the 26th. There's 2 planets, Saturn and Neptune are both 10 to the 26th. But Neptune is only 1 times 10 to the 26th. Saturn is 5 times 10 to the 26th. So we'll go Neptune smaller than Saturn. So Neptune follows Uranus. And then Saturn is the second largest planet. Second highest mass will go in at 7. Okay, and this is what I'm seeing, right? This is what you're writing down. Typing down. Maybe in a, I don't have the DNA sheet up. Making a chart in your DNA sheet, in your box. Probably a good idea. 8 is obviously going to be the last planet, largest mass, 10 to the 27th, Jupiter. Largest planet, sometimes considered a failed star. Not enough mass to actually have fusion happen. Very, very low in mass in order to have that happen. Rotation is next. So the shortest day to the longest day for that object. So the shortest amount of time to do one full rotation, spin once on an axis, right, to the longest day. All right. Again, we want to see if it's positive, it should go Mercury to Jupiter. If it's negative, it would go Jupiter to Mercury. If it's no relationship, we would have a random listing of our planets, right? So let's take a look. We want to do the shortest day, right? Which one has the smallest decimal? Well, the gas giants are all under half. Well, except for Uranus and Neptune. They're all under 1, I should say then. So they're all less than 1 day. So they all spin faster than 24 hours. Jupiter and Saturn are less than 12. Uranus is almost 3/4 of a day on Earth. So we'll go with Jupiter's first, 0.38. So almost 38% of an Earth day. After Jupiter, the next shortest day is from Saturn. After Saturn, our next two options, Uranus and Neptune. Neptune's shorter than Uranus, but longer than Saturn and Jupiter. It's larger, right? So far, the list is working almost backwards, right? Here's Jupiter. Here's Saturn. Neptune. Need a teal for Uranus. There we go. And there's Uranus. So far, the list is working mirrored. It's working opposite. We know opposite leads us to a negative relationship. So Jake Rainey was predicting it's a positive relationship. The more mass, the longer the day. I don't know if that's how it's going to work. We'll go back to our data. Use the inner solar system. It's okay to be wrong as long as you figure out, why you're wrong. Learn from your mistake. After Uranus, the next shortest day is going to be Earth. After Earth, almost exactly a day though, 1.03, 3/100ths of a little extra time to rotate is Mars. And then after that, we have Mercury and then Venus. Mercury has 56 Earth days to do one rotation, and Venus takes 117 days. That is ridiculous. It's almost the same size as Earth. My prediction, it would be maybe a little more than Mars, but not 117 days. So that's what we're going to call is an outlier. Venus is an outlier. All right. So let's finish up the relationship chart. I got to put in Mercury and then Venus. Pop back over here. Here's the Earth. Mars. We skip in Venus, and we jump over to Mercury. So for the most part, for 90% of this chart, it is opposite. The higher your mass, the higher a planet's mass, the shorter the day, the shorter length of time it takes to do one rotation. Venus, however, doesn't follow that. Venus is an outlier. It's an exception to this rule, to this relationship. And so scientists now then, after they answer this phenomenon, will go on to answering, well, why does Venus have such a slow rotational time? And then that's the next scientific question. Another experiment, more information, more research to answer that question. And that's how science works, right? So the relationship, let me not do that in purple because it might confuse you. The relationship is positive between mass and rotation. Okay? As mass increases, then rotation decreases. Or, as mass decreases, then it takes a longer period of time to turn on the axis. Okay? I'm sorry, I just did positive. Just looking at chat. Rainy. It's negative. I'm sorry. This is doing the opposite. Variables work opposite. Alright. Well then, how about the outlier? How about Venus? Any reason why Venus doesn't follow this rule? Anybody who did Venus? Anybody who's familiar with Venus? Oh, I'm blocking it. I moved it. Just waiting for the stream to catch up. Doesn't orbit the sun clockwise. It still orbits the sun, or revolves counterclockwise, but we're not talking about revolution here, Hayden. We're not talking revolution. You're on the right track. Let me write this a little clearer. Rotates clockwise. Outlier is Venus. The only planet that rotates clockwise. Remember, everything else rotates counterclockwise, even majority of the moons and asteroids. Well, they definitely revolve, but many of them rotate. The moons. I don't want to speak for the asteroids. So the outlier is Venus, the only planet that rotates clockwise. So it's slowly going the opposite direction. It's slowly going the wrong way. And so the initial thought would be, hey, an object must have hit Venus. Kind of like Uranus. Uranus is on its side. It's on that 90-degree axial tilt. An object did smack Uranus and turn it on its side. But to do the same thing for Venus, the object would probably destroy Venus. Uranus is a gas giant, it's very large. Venus is a terrestrial inner solar system planet, and any kind of collision like that on that kind of scale would destroy the planet. So it's not because an object hit it. Venus, besides any of the gas giants, has the thickest, largest atmosphere. And as it's moving, as it's rotating, the planet itself rotates against the atmosphere. It is going to cause drag, it's friction, and it's going to cause it to slow down, and eventually, that's the current theory, turn the wrong way. So, kind of erase this period. The only planet that rotates clockwise due to drag of its incredibly thick atmosphere. So it's good to understand the outliers and the exceptions because then it helps you understand your rule a little more clearer. So if we're talking about exoplanets, like we are this week, I'll come back to this in a second. Yesterday's question on Monday asking you what is the relationship between a planet's mass and its surface gravity seemed to be the higher the mass, the higher the surface gravity, unless you're a very, very, very low dense planet. And then relationship between a planet's mass and its rotational period seems to be negative. Okay, the higher the mass, the shorter the day. So if we're talking exoplanets, if an exoplanet has really, really high mass, I'm going to assume it has a short day and it has high surface gravity. So you can start to kind of predict what the properties are of these exoplanets. This is especially important for people who are doing application A, the CER, because you are researching criteria on what makes a planet habitable, what makes a planet similar to Earth. And so you have to do a little bit of research, probably about Earth itself. And I'll get into the criteria when I start talking about the GSA in a few minutes. All right? Any questions so far? Make sure you ask them in chat. Send them to Remind. So, this quick little video. Our 8 planets. This is the actual time. This is not a, like I put in the table, this is not a fraction of an Earth day. This is actually how long it would be in Earth hours, right? So now, each one of these bands is the 8 planets. Neptune's kind of cut off, all right? But we have Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and then Neptune at the South Pole, all right? This is not an actual picture, all right? This is not this is not an exoplanet. This is not anything that you're going to use as a source. Other than that, it just shows you, comparison-wise, the speed of rotation for each of these planets. And it shows you how Earth and Mars are pretty much locked together. Mercury and Venus are barely budging. Jupiter and the Great Red Spot are zipping around multiple times. Saturn's very fast. Uranus is on its 90-degree tilt, so it kind of looks like it's going clockwise, but it's not. And there's Neptune underneath it. So obviously the big striking things are Earth and Mars are very close together, Jupiter and Saturn whipping around, and then Mercury and Venus are very slow. And the other gas giants are kind of just moving in between the larger gas giants and Mars and Earth. So it's a cool way to visualize something that we can't usually see. And that's DNA number 2. DNA number 3 tomorrow, we'll take a look at distance from the sun and temperature. You'll have 6 questions on your DNAC on Thursday. Keep emphasizing Thursday. Three of those questions will be about a relationship. 3 of those questions will be a follow-up about the relationship. The exceptions to the rule. So know the exceptions, know the rule. All right? All right, the GSA. Yesterday, you had to pick an application, either A, B, or C. And then with that pick, you then had to answer the first initial question to help direct what you're doing. If you're unable to find the materials for application B, you're going to have to change your application. After today, you are locked into your application. You can't be switching around because you need the time to complete the project that you're working on. All right? Again, application A is writing a research CER. gathering data, presenting your findings. Application B is doing a pre-designed experiment. You're not picking out the independent variable. You're not designing your own project. I kind of have the directions for you. You just execute. Okay? Application C is a theoretical prototype of an interstellar spacecraft. What hurdles would you have to overcome? What constraints do you have? And how would you get a spacecraft to the next closest star, Proxima Centauri? Application B is looking at the spectra of sun-like stars. What's a spectra? Picture the light coming from a prism and it not being a perfect rainbow. There being black bars in a perfect rainbow. Those black bars are absorption lines. If you watch, and if you're doing application B, watch, does the sun have a shadow? Because there's more information for you there. You need to watch that video if you're going to do application B. Gives you some good background information on what a spectra is. And then your research CER is, again, researching habitable criteria for a planet outside Earth. All right, what would a new home for humanity need to look like? All right, so you picked your application, and hopefully you answered your first question, your direction question. So I'll kind of hit each criteria. You guys are working. Listen as you hear your application. I would start deleting the letter and the color that you are not doing. So if I'm doing application B, I can two-finger click this table and I can just hit delete table. Application C, two-finger click, delete table. And now my phase 1 is just my application B. I'm not worried about anything else because I'm only doing one of these. I'm not doing all three of them. Alright? Same deal. I'm doing B, so I'm going to delete this table, and I'm going to delete this table, right? So when I go through my phases, only thing that should be left is blue. I gave blue to application B, all right? So delete things that you don't need. It's just extra information that might confuse you, and it kind of just makes the document longer than it needs to be, right? So you're customizing the document according to what you're doing. Hopefully that's good so far. I think that's straightforward. Hoping. Application A. You are starting phase 2 today. Evidence and data are the supports in building a well-written argument. You are trying to establish your point, your research, your idea, which is your claim, as the best possible avenue, best possible direction in a research-based approach. So what are your directions? Kind of gets cut down. I didn't think it went on to the next page, but keep in mind it goes down. Direction, you are gathering data on exoplanet habitability from at least 5 different sources that provide accurate and reliable information. So again, what are those sources? URLs, websites, the link at the top of a page that end with .gov, .org, or .edu. Government websites, for the most part, are very reliable. They need to be because they have to guide the general population. Some government websites are more reliable than others now. All right. NASA is probably your best. .org, different organizations, and then .edu, different universities and colleges. They provide information to their students, or many of their professors are research professors and research scientists themselves and produce information for the college or university. So those are your 3 primary ways to get an accurate, reliable source. Some .coms are accurate, reliable if their main mission is to provide information, but still, you kind of want to avoid them because they would have a bias because they do receive money, probably from ads. So you don't want people taking money from ads and then having them direct the information, right? You want free information. Your best bets are .gov.edu. All right? You are going to copy and paste your source, and you're going to provide citations. So I kind of flipped it from Tour the Solar System. Tour the Solar System, you pasted your source to the right, and then you put information bullets on the left. No big deal. Just paste and then cite. Can you cite or just copy and paste from the website? Just like Tour the Solar System, yes, you can paste information from the website. However, when you start going forward, one way or another, you're going to have to start putting things into your own words. Okay? So if you're just going to paste information from a website, you're just delaying the inevitable. All right? So you can do it. I'm just saying, maybe start practicing putting into your words here so the next section becomes easier. The next section being an outline, right? That's got to be in your own words. So you can paste from a website, but eventually this information's got to be in your own words, your own paraphrasing. All right? So sources here, and then information. What are you looking up? Because I kind of helped you on Tour the Solar System. This is a little more open-ended. Focus, sorry for getting cut off, focus your research on axial tilt, distance from the star, type of star, habitable zone, and mass. Habitable zone is something we haven't really talked about yet, but it is the distance from the sun where liquid water is possible on the surface. And I say sun, I'm going to say star. Distance from the star where liquid water is possible on the surface. That sounds straightforward. Here's the problem. The habitable zone of our star, our sun, is different from the habitable zone around Proxima Centauri. And that habitable zone is different from the habitable zone of a star like Betelgeuse in Orion. Why? Our sun is a main sequence yellow dwarf. So type of star? That means our star is kind of small, which means it doesn't burn its hydrogen up really fast. It will last a long time. So it's kind of on the small side, but it's in its middle life, its main sequence. It's not towards the end of its life. It's not towards the beginning of its life. It's very stable, and it produces enough heat to be useful, enough light to be useful, but not enough to fry the planets in its system. And it's going to last a long time because it's on the smaller side. If it was bigger, it would burn through its energy faster. Think of like a fire. Is it easier, a campfire, is it easier to keep a small campfire going for a long time? Or is it easier to keep a raging inferno going for a long time? So that's kind of how a star might work. Campfires and stars are limited by the same physical laws. You need energy. Rage. No raging. Okay? So types of stars exist. So you got to do a little bit of research on types of stars. All right? Red dwarfs, blue supergiants, red supergiants, T Tauri stars. Those are baby stars. There's all types of stars. What type of star would we want best? Probably a sun-like star, right? Okay. Distance to make it a habitable zone, axial tilt. So you're kind of looking for things on the Earth and then comparing it to another planet. So I would begin by find these for the Earth, which means you already know the tilt for the Earth, 23.5 degrees, right? Find a source that says that. Yes, you can use Earth-Sun geometry. That's a source from class. And then go on to finding other information. So there is 1, 2, 3, 4, 5 different categories. 5 different categories, and you need 5 sources. Might just use a different source for each category. All right? That's application A. You got questions? You let me know. Mr. Downey says, we got a problem. The sun is not out right now, and I have to use the sunlight for phase 2 in app B. Did you already build your spectrometer? That sounds like you already built it. Nikolai's in sunny California. Yeah, you're lucky until guys go back into a drought again. That'll be unfortunate. Hopefully it doesn't come to that, but it's not looking great. Not yet. So we're doing this over 2 days. So again, guys, if you're doing application A, do 2 or 3 of these today. Do 2 or 3 tomorrow. Okay? No, you do not have to record data today. I'm getting into it. Let me go through this, see if it answers your question. All right? I don't want to jump ahead. So you have 2 days to do phase 2, today and tomorrow. All right? Application B, the hands-on experiment. So if you're doing A, start doing your research right now. Don't be bothering listening to B or C. All right? Experiments require data, qualitative and or quantitative. Qualitative is numbers, is qualities, traits, characteristics. Quantitative is numbers. Mass, volume, finding density, right? You will be looking for qualitative in this experiment because you're going to be observing the qualities of light from different sources. All right? So, to determine the effect, if there's any, of the independent variable on the dependent variable. Our independent variable are going to be light sources. Our dependent variable is going to be the spectra. So, let me just make that as a comment so you see that. Independent variable, the different light sources, and then the dependent variable, their spectra. Complete the procedure using the associated materials and data for later analysis. So if you go back to your first question, this was kind of phrased as a hypothesis, right? If light can be used to identify its source, then that's due to, if light can be used to identify its source, then we can look for other sun-like stars because light is based on wavelength, and there's different wavelengths, right? So you, in application B, are the astronomers looking for sun-like stars. Application A, these are the planetary scientists looking for planets around stars to see if they could harbor life as we know it, could harbor humans. You guys would be directing the planetary scientists because the type of star, probably the best, are sun-like stars. So what's a sun-like star like? Do a little bit of research, right? Well, then you guys are like, well, here's a sun-like star, here's a sun-like star, here's a sun-like star. So application B are the astronomers. Application A are the planetary scientists, the astrobiologists, the planetary scientists. Okay? Application C, you guys are the engineers. You're trying to solve the problem. Cross space, right? We'll get to that in a little bit. You need to have, in order to do this, if you don't have this, stop. Cereal box, scissors, half a blank CD, because you're just going to insert half in. All right? Non-clear tape, so like masking or duct tape, and then different light sources. All right? Your procedure. You cut a small square hole on one of the sides. That's your viewing window. Cut a 60-degree slit for your CD, DVD, game, whatever. You're not afraid of getting scratched. You know, some games now in this day and age, you guys can actually get digital versions. So, I mean, those games are kind of pointless now. For example, I know a few of you play Destiny 2, right? Destiny 2 just went all digital. You don't even need the disc anymore, so throw Destiny 2 in there, right? Not like it's worth playing now anyway. A little boring. Besides the shade, all right, step 3, 4, already mentioned all those. 5, use the tape to seal in any of the holes. Make sure you cut the slit opposite the disc. All right. I'm going to grab my prototype after I go through C, just so you can kind of see, literally, that you want that to be as clean as possible to get this to work. All right. So this is the side view, hole over the top, 60-degree angle, insert the disc in, viewing for the light source over here. All right. You just want to slit because you want to focus the light onto the disc. All right. And then you'll see a rainbow, and that rainbow will look a certain way. There'll be a certain color from left to right. You would draw tomorrow what the spectra looks like for each of these sources. And then colors with major absorption. I'll go over this again tomorrow. What colors have black lines in them or are missing colors? All right. So where are we missing colors? What does it look like from your little viewing window? All right. You need one additional source of light to get a 4 out of 4. All right. Sunlight, it's still light outside, so you can still technically use sunlight. It's just not going to come out very well. So yeah, Downey, tomorrow is probably going to be more sunnier than it is today. Use tomorrow. All right. But do not point it directly at the sun. Okay? If you need help, obviously ask questions, but here I linked in a video of a doctor working at, I think, Oxford? Yeah, University of Oxford, and he's building his own spectrometer. All right. He has his cereal box. He did it vertically instead of horizontally. Viewing window, slit, CD. He used aluminum foil to make that cut more clean, and that will allow better spectra. So he points at a light bulb. Different lights have different spectra. You can kind of see. I don't know if it'll be that clear, but different lights have different spectra. Different rainbows and black lines in them. All right? So use this video to help build it if you get stuck. I'm hoping it's pretty straightforward. All right? I try to film my own version, but not having a tripod for my camera or phone, it's tough. I was trying to cut while trying to film. Didn't want to drop my phone. Plus, I was also filming upside down because I'm right-handed. For some reason, iPhones, if you film with the record button on the right side instead of the left side, it flips it upside down. I don't know if Steve Jobs was lefty, but unfair. Anyway, again, I'm getting off track. That's application B. You are only doing, I suggest, to kind of break this up, only build this today. Build it and test it. Build it and don't do this yet. Just test it with a ceiling light to make sure you can actually find the spectra. Okay? So build and just practice. Maybe that's a better way to phrase it. Build and practice today. Don't bother trying to actually do the data collection. Do this tomorrow. So this, due on 4/29. Okay? Do that tomorrow. Practice building today. If you got some good pictures, you can send them my way by email. That'd be pretty cool to see. Put them on stream. All right. Oh, great. The mailman's here. His name's Marvel. Can you use the camera that you used for the live stream? No, I mean, I probably could have used my laptop. It's not a bad idea, it's just been tough to see. Because it's like you guys using your Chromebook camera. You gotta like be in front of it while you're filming with it. It's tough, but not a bad idea. Oh, could you use it? I don't know if you're saying, could you use it to record yourself? Or if I could use it for myself? You're full of good ideas. Yeah, you are, but we'll just use the Oxford Guys video because now we're already in the middle of doing the assignment. So maybe next time I'll try and set up a little studio. Alright. Application C. Alright, so if you're doing B, you go right ahead, you start building. Okay? Application A, you guys should be researching. So A and B, you guys are at work, right? Application C, in brainstorming, no solution is a bad solution. So you're brainstorming right now. Yes, you may think of some not so great ideas when you brainstorm, but in the moment, at the time, no solution is a bad solution because you got to look at all possible avenues for a problem. All angles. It's called due diligence. Okay? Think about, like, you know, if you like football, different coaches are going to, you know, interview and look at different candidates for the draft. So, for example, Bill Belichick is famous for doing interviews with top quarterbacks coming into the draft. Why? He had Tom Brady. Why would he need to do that? His pick's always very high. They're never going to get him. Very true. However, why does he interview top quarterbacks? Because it's like a free scouting report when they face that quarterback down the road. So, do your due diligence. Okay? No solution's a bad solution until you start evaluating it. Alright? Find all possible research-based solutions to the problem. This provides due diligence in the engineering process. See, I forgot to even put that in there. You want to do your due diligence. Alright? Gather data on interstellar travel solutions from at least 3 sources that provide accurate and reliable information. That means things with .gov, .org, .edu. So this is a little less research than application A. However, it's because these ideas are a little more complex. And if you have questions, please let me know. Okay? I know NASA already has at least 1 or 2 solutions. So you go to NASA's website, you go to nasa.gov, and you start searching interstellar or interstellar spacecraft, interstellar travel, and you'll probably come up with 2 ideas already. I can think of 2 ideas off the top of my head. One of them is about sending a probe to Proxima Centauri, so a non-human spacecraft. And the other one would be using something like a warp drive, I guess you could call that. So Star Trek and Star Wars are a little different in their space travel. So you're trying to think of like the better analogy. You're probably thinking more along the lines of Star Trek, warping space around you to go faster than light. All right? Is that even possible? There's some theories from NASA, okay, based on some pretty high-grade physics and other research universities again. So you're going to find 3. I gave you 4. If you find a 4th, to get 4 out of 4 points, give me as much information as you can, right? Just the name of the solution in the box to the left, and then describe the solution and give me your source with your information. So you just kind of just paste the link after what you describe. All right? So in application C, you are imagining first. You're imagining what other scientists have come up with so far. Are they even close to doing it? No, they're not. But is it a starting point? Maybe. Hike asks, so we are finding solutions to our problems we came up in on part 1, or just overall solutions for an entire spacecraft? So your problems, your constraints, just trying to see, yeah, your constraints from the first question should go into your solutions here later. So this is what I want you to do, Hike. You find in general 3 sources, 3 ideas, 3 to 4 ideas, right? Tomorrow, and then in phase 3, you're going to see which ideas actually address your problems from the first question, right? So you're going to see which problems in part 1 can be addressed by part 2, and then you're going to come up with 2 possible designs. Does that make better sense? Part 1, you made up your constraints. Part 2, that makes sense? Good. Part 2, you're looking for possible ideas, but then you're going to narrow them down for a real solution in part 3, or 2 possible solutions. All right? Your solutions. And then your final solutions in part 4. All right? Again, this takes 2 days, so I'd find 1 or 2 ideas today for part C, for application C. And then tomorrow, find another 1 or 2. So phase 2 takes 2 days. Today, tomorrow, we'll start phase 3 after your DNAC on Thursday. All right? Hayden, I saw a video about how a warp drive would work. That's kind of what we're getting at. If it's from a reputable person, source, scientist, physicist, you could link that in here. Phase 2 takes 2 days. Yep. I'm thinking phase 3 takes about 2 days too. Phase 4, about 2 days. Puts us at the end about midnight before May 6th, which I think I have this set as a deadline anyway. All right, so don't get bogged down with the other parts yet. All you're focusing right now is doing half of part 2 for today. Research, building, research. Guys have any questions? Each day I'll kind of go over what you should be doing for part A, B, and C, application A, B, and C, as we move along. All right? Again, I'm anticipating this due in a little over a week, May 6th, before midnight. Okay? So again, taking your time, doing your DNAs. Tomorrow is DNA number 3. And then DNAC on Thursday. So, final summary. Today, starting phase 2, doing DNA number 2. Tomorrow, doing DNA number 3, finishing phase 2. Thursday, take the DNAC, start phase 3. Friday, little academic help by Eric. And then also, going to keep plugging it in, we have our mighty meetup at noon. So definitely show up. Please. You can see each other. And enjoy what you have left in middle school. Alright? Miss Kildoff, you still need to think of a movie. So again, make sure you guys have any questions, you send them my way, remind or email. Check it throughout the day, help you when I can. If you guys got no questions, I'll see you later. Have a good Tuesday. Bye Ryan. Bye Ezra. Bye Charlie. Bye Hike. Bye Abel.